Welcome to the next in the series of how-to videos for you. I hope you liked the first one. I thought I would do some work on nuclear physics, atomic physics today. So here's a question on nuclear fission and fusion. So you should know the difference between fission and fusion. And unusually, you need to be careful how you spell these, because fusion with two S's is possibly misspelling of fission. So you need to spell them correctly. Spelling isn't normally terribly important, but it is in this case. So use the correct answer from the box to complete each sentence: Geiger counter, nuclear reactor, and star. Nuclear fission takes place, well, that's in a nuclear reactor. We don't do fusion in reactors on Earth just now, although we're trying very hard to do that. And nuclear fusion takes place within a star. If you're not sure about this, the Geiger counter is something you use to detect radiation. And what's happening in there is actually ionization, neither fusion nor fission. One way in which the process of nuclear fusion differs, well, fusion is the combination of smaller like nuclei that's fusion, whereas fission is the splitting of a large nucleus to make two smaller nuclei and release energy in gamma rays. So that's the principal difference. Fusion requires very high temperatures, whereas fission does not. In a star, you have high temperatures and high pressures, and so you can do it at a lower temperature. On Earth, we have to try and do fusion at a higher temperature to make up for the lower pressure that we're doing it at. And that means you're doing it at 100 million degrees centigrade, which is hot. Part B, the following nuclear equation represents the fission of uranium-235. Use the information in the equation to describe the process of nuclear fission. For 4 marks, we have to make 4 points here. So we have the uranium nucleus is absorbing a neutron. It is becoming uranium-236. You see how the mass number has increased by 1 because it's absorbed this neutron, but the atomic number has not changed because there are no more or less protons here. This uranium nucleus here, the 236, is now unstable. It can't stay like this. And so it breaks up into 2 smaller daughter nuclei, releases 2 more neutrons, so there's 1 and 2 more, and energy, and also gamma rays. So use the information. So the uranium-235 absorbs a neutron. Becomes unstable, breaks up or decays into 2 daughter nuclei, or you could say smaller nuclei, but we like to use key terms, and daughter is the term we use. Releasing 2 more neutrons. energy and gamma rays. So definitely 1 mark there. 1 mark there. 1 mark there. Definitely a mark there. We have to be careful not to say stuff that we are told in the question. So this doesn't come from the question. The neutron is here, but doesn't say what's happening to it. So we're adding something with this. It doesn't say it becomes unstable. So we're adding something with that. Daughter nuclei, well, this is adding something. You could say that these are smaller nuclei because they clearly are 141 versus 236 and 92 versus 236. And the gamma rays, well, that's something that doesn't occur up here at all. And so it's worthy of credit. So those are the 4 points that I would choose. So finally then, part 3, an isotope of barium is barium-139. Barium-139 decays by beta decay to lanthanum-139. Complete the nuclear equation that represents the decay of barium-139 to lanthanum-139. So beta decay. Well, beta we know is 0 minus 1. So because it is an electron actually, and the electron comes from a neutron decaying into a proton and an electron. You can make sure you're right about that because you have to have mass conserved and charge conserved. Neutrons have slightly more mass than protons, and the difference is the mass of the electron. You might not know that, although it's helpful to know that. However, you do know that charge must be conserved. We have 0 charge over here. We have a positive charge here. We have a negative charge here. So 0 plus 1 minus 1. The total here is 0. Charge is conserved. So this is an electron, which means when this decay occurs, you're going to have 1 fewer neutron than you had before. So we need to look up the mass number of barium, and hopefully you will have a periodic table in your exam for this, but I don't have one to hand. So I'm going to Google the atomic number of barium. Which is 56. So we have, sorry, yes, 56. So because there's an additional proton than we had before, this will go up to 57. 57 minus 1 is 56, so that balances. The total number of particles hasn't changed in the nucleus. We've changed a neutron to a proton, so the mass number will not change. So that's why your beta has a mass number of 0. So there's your answer. Knowing that beta is 0 minus 1, and this comes from, this is actually what's happening, then these two numbers have to add together to give you this. So knowing, looking this up to be 56, we know that must be 57 because that is minus 1. Hopefully that helps.